Hello, welcome to The Naked Scientist with me, Chris Smith, and also with Kat Arney.
Now, are you sitting comfortably? Well, you might want to stand up because we'll be hearing this week why, in health terms, sitting is the new smoking. We're also taking a look at the science behind weight loss and why shedding those extra pounds is so difficult.
And you'll be pleased to hear that I am indeed standing up and will remain so for this entire show. Now, meanwhile, coming up in the news, why colds really do prefer the cold, why most of the world's fossil fuels need to stay in the ground if we're going to meet climate change targets, and home from home, how scientists have discovered Earth's twin deep in outer space.
The Naked Scientist podcast is powered by ukfast.co.uk.
It was dismissed by doctors for decades as a myth, but now scientists have proved that the winter weather really can increase your chances of catching a cold.
Yale University's Akiko Iwasaki has found that when the cells in our noses are infected with viruses, they sound a chemical alarm to help other cells to fend off infection. But at lower temperatures, this doesn't work so well, giving an attacking virus an advantage and partly explaining why colds are much more common in winter.
It's been known since the 1960s that the common cold virus, or the rhinovirus, replicates at a cooler temperature found in the nose. However, it was not known why the virus replicates better in this cooler temperature.
When you say the virus replicates better in the cooler temperature in the nose, are you saying then that because the nose is colder, that the virus grows better?
Yes, the virus grows better in the nose temperature.
How do we know that?
Oh, this was done in 1960s when people used to try to culture the virus from the nose of people with the common cold symptoms. And they couldn't grow the virus well at the typical temperature of 37 degrees. But when they reduced the temperature of the incubator to 33 degrees, the virus could grow.
37 degrees being normal body temperature.
That's correct.
Would the inside of the nose normally be about 33 degrees then, because it's exposed to cold air?
That's correct. Yes, typically 32 to 33 degrees in the nose.
And had everyone concluded that the virus wouldn't grow because the virus prefers, in inverted commas, a cooler temperature? Was that their deduction, but they just didn't know why?
That's correct. And many studies have been done in looking at whether there is something about the virus that grows better in the cooler temperature of the nose. For instance, people have taken apart bits and pieces of the virus to see whether each component of the virus works better at the cooler temperature. But none of these studies have revealed the mechanism for this.
So they all drew a blank?
Right.
Was your suggestion then that, well, if it's not the virus, perhaps it's actually the person?
That's right. So we started to look at this question from a different angle, how the viruses are detected by the immune system in general. So we've been studying these molecules known as sensors that detect virus RNA inside the cell.
This is the genetic material of the virus, isn't it?
Right. So the rhinovirus has a RNA genetic material inside of it. And the host cell can detect the presence of this RNA inside the cell when the virus grows inside the cell.
A bit like a sort of tripwire. There's a chemical tripwire. The cell says, aha, I've got this funny genetic material in here that shouldn't be here, so it knows that it's been infected.
That's correct. And these molecules are collectively known as sensors. And so we have mice from which we've taken away these sensors. And so we can study the importance of each of these sensors in blocking the virus from growing. When we looked at the ability of the virus to grow, in the absence of these sensors, they could now grow even at the higher temperature of 37 degrees, indicating that it's not the intrinsic property of the virus, but it's the host immune response that dictate which temperature the virus can grow in.
Why hasn't the virus, given how common these rhinoviruses are, I guarantee everyone listening to this has probably got a cold or they're getting over a cold, probably caused by rhinovirus right now. Why hasn't the virus evolved a way around that? It seems so simple because it's literally stopping it doing what it could do. It could grow all over the body if it were to surmount that temperature problem then.
That's correct. In fact, that's a very good question. We think that the rhinovirus actually prefers to replicate in the nasal cavity because it is easy to transmit the virus from the nose to the next person by either touching the nose or sneezing or other means.
Is it not possible to come up with some kind of drug or a nasal spray that could tweak the sensors in our cells in the nose, or even give us an artificial sensing system so that tripwire that enables the cells to detect a virus growing in our nose goes off at the lower temperature better?
Yes, that would be an innovative way to deal with this problem. But there's another problem with this, is that we found not only the sensors of the virus don't work as well at the lower temperature, but also the interferons that are produced as a result of the sensing don't stimulate the neighboring cells as well. So these interferons are molecules that are secreted from infected cells to try to alarm the neighboring cells from becoming infected by the virus.
Like a burglar alarm going off when there's been a smash and grab in one cell by a virus.
That's correct. That's correct.
They're telling the cells next door, watch out because there might be a virus in the neighborhood.
That's right. And usually this alarm works very well. But what we found is that in the nasal cavity temperature, the alarm system also doesn't work very well. So you would have to overcome both of these issues in order to prevent the virus from growing in the nose.
It sounds to me like we're stuck with the common cold then. The way you're telling this, it sounds like really actually we're going to have to live with it.
Maybe. The other way to deal with it is, I guess, to warm up your nose to the temperature that's not permissive for the virus to grow.
What would you recommend then? A large whiskey or something to give you a nice warm red nose?
That's one possibility. I don't know how much the whiskey increases the nasal cavity temperature. I don't think anyone's measured that.
Nonetheless, I'd be very happy to help with that particular experiment. That was Akiko Iwasaki from Yale University over in the States. There you go, Kat. You're going to have to warm your nose up to get rid of those colds that keep plaguing you.
I will certainly try. Now, talking of temperatures, climate change and global warming are strongly linked to rising carbon dioxide or CO2 levels in the atmosphere. The world's politicians have agreed that a 2 degrees Celsius rise in global temperature is as much as the world can take, based on the best scientific evidence that we currently have available. At the same time, there are still huge reserves of fossil fuels, that's oil, gas and coal, which all release CO2 when they're burned.
And if all of these reserves are extracted and burned, it would produce so much CO2 that it would push us right over that 2-degree limit. So, the world's fossil fuel producers are going to have to make some tough choices about what and how much they extract and burn. According to Christoph McGlade at UCL's Institute for Sustainable Resources, they're going to need to leave a lot of this stuff in the ground if we're going to hit that 2 degrees target, as he explained to Kat.
This model looks out into the very long term, out to 2100, and says how can we best meet all of our energy needs in the future in a global context. It finds the cheapest way of satisfying all of the energy uses that we might have in the future. How are we going to heat our buildings in the future? What we're going to use to drive our cars? How are we going to produce all of the industrial goods? And for this work, what we did was we imposed this 2 degrees constraint on the model. So we said that carbon emissions resulting from the use of oil, from gas and from coal cannot result in a temperature rise which is above the 2 degrees target.
And so when you look at this, how much can we use of the stuff we know is there in the earth?
Of the coal reserves, only about 20% of these can be used. So that means that 80% of current coal reserves have to stay in the ground if we don't want to exceed 2 degrees. For oil, it's about a third needs to stay in the ground, and for gas, it's about half of what we think is currently economic to extract has to be left in the ground.
This seems pretty significant because obviously there must be energy companies who have made predictions, who are going out looking for more oil and stuff in the ground. We talk about fracking, talk about exploiting the oil that's under the Arctic. It's a bit difficult to say to them, you know what, guys, you can't even take the stuff that you think you've got.
Absolutely, and there's a big inconsistency currently between what trajectory that the world is currently on and what people have agreed to. So yes, the fossil fuel companies which are continuing to explore for new resources need to be aware that this is completely inconsistent with the 2 degrees target.
Oil and gas and coal reserves that we have aren't equally distributed between all countries. So how do some of the things shape up in terms of which countries have to be on the strictest carbon diet?
Generally, those regions which have the most resources currently are going to have to go on the biggest carbon diet, as you call it. For coal, the United States and Russia can only use less than 10% of their current reserves. In the Middle East alone, there's around 260 billion barrels of oil. That's the entire oil reserves of Saudi Arabia, which need to remain in the ground if we don't want to exceed this 2 degrees.
One of the things that comes out of your paper is that we can't even burn the resources that we know that we have, and yet companies are exploring in places like under the Arctic. We're looking at technologies like fracking, which is very contentious at the moment. Your calculations would suggest that this is basically a waste of time.
Yes, so within the model, we identify all of these different resources that are out there, and you mentioned the Arctic, and we can look at, under this 2 degrees scenario, which of these resources are actually used. And the results suggest that actually the Arctic oil and gas, and there might be quite a lot of oil and gas up there, isn't required if we want to stay within 2 degrees. Some of the other sources you mentioned shale gas.
So that's from fracking.
From fracking, absolutely. There is some potential for that to be used, particularly if we have a rapid reduction in coal consumption in the future. Some gas will have to come through, and some of that gas can be shale gas. However, if countries such as the UK decide to develop its own shale gas resources, it has to be aware that as a result, someone else somewhere else isn't going to be able to use all of their reserves. So there's always this trade-off between if we exploit here, someone else has to not exploit somewhere else.
Christophe Macleod. Meanwhile, UCL's Paul Ekins, who also worked on that analysis, told Kat what else needs to happen to make it a reality.
It's an enormous challenge, because countries quite legitimately regard these resources as theirs, and the decision whether they use them or not is their decision. They will need to agree not to use some resources somewhere. And the countries that agree not to use their resources, they will probably wish to be compensated in some way. Those kinds of arrangements need to be on the table in the climate change negotiations.
Climate change is a global problem. It needs all the leaders of all the countries in the world to work together. Some countries say, well, no, we want to carry on, we want to develop, we want to use our resources. Is there hope, realistically, that countries can actually work together and come to these solutions? What's your personal feeling on this?
Yes, I'm very hopeful, because I think increasingly it will become obvious that climate change is something which they very much need to avoid. It may be true that money makes the world go round, but money doesn't go very far if you haven't got a livable climate.
The projections in this paper go up to 2100. If you could maybe paint me a picture, perhaps even over the next 20, 30, 40 years, how you would like to see things changing.
Yes, things do change quite dramatically in the world in which we live over a period of 2 decades. So, anyone who's more than about 40, if they look back 20 years, many of the things they now take for granted were not even dreamt of. And it is my firm conviction that if we were to bite the bullet of low emission energy systems and agriculture, by the time we got there and looked back, we would wonder why we had thought it was going to be so painful. Because many of these technologies already exist. We can invest in them. A lot of them are not much more expensive than the technologies they're going to be replacing. So my dream scenario is that both in the UK and globally, governments recognise the urgency of this issue, and they start to do things like pricing carbon, which will send investment in a quite different direction so that these low-carbon technologies become much more widely installed, emissions start to fall, and publics become much more confident about the kind of trajectory that is possible.
Let's all hope that that comes true. That's UCL Professor Paul Ekins.
Still to come, a new antibiotic which could be a game changer in the battle against drug-resistant superbugs. But first, a discovery a lot further from home.
Yes, this week, scientists using the orbiting Kepler telescope to look in deep space for other Earth-like planets announced that they found the closest matches yet for our Earth. The nearest is still over 500 light-years away, slightly larger than Earth, and the sky is red, but otherwise it looks ideal and the temperature's just right for liquid water to exist. Greer Jackson spoke to the project leader Willie Torres from the Harvard-Smithsonian Center for Astrophysics.
Kepler is a spacecraft launched by NASA in 2009 that was designed to stare at about 100,000 or 150,000 stars for 4 years continuously, looking for changes in brightness that might signal the passage of a planet across the disk of the star.
And how do you know that they're planets and not something else transitioning past the star?
There are many other phenomena that can mimic the signal. One example would be an eclipsing binary, a pair of stars that go in front of each other. So it's up to the scientists to investigate the target in gory detail and determine the likelihood that it is a planet as opposed to some other phenomenon that has nothing to do with a planet.
And that's what you've been doing with your study just released this week?
That's correct. Of the 12 candidates that we investigated, we were able to confirm 11 of them as being true planets with a very high level of confidence. And this essentially doubles the number of planets that are in the habitable zone of their stars and are similar to the Earth in size.
What's so novel about this study? Because I'm sure scientists have identified, I think, something in the region of 1,000 exoplanets. So what's different about your study from all the other previous ones?
Well, I think the main result is that 2 of the planets that we have validated are the most similar to the Earth of all the planets known so far, if you consider both their size and the energy they receive from their star jointly. So if you consider those 2 conditions that are required for habitability, these 2 are the most Earth-like planets that we know of so far.
And do these 2 planets, these particularly promising ones, do they have a name?
They have numbers. One of them is Kepler 438b, and the other one is Kepler 442b.
Do you have pet names for them? They're quite unimaginative, as they are.
Yeah, unfortunately, that's the way this works. We have so many of these now that you have to give them numbers.
How far away are these planets that we're talking about? Surely they're hundreds of light years away, no?
The range of distances of the 8 planets that we have validated ranges from about 500 light years to about 2,500 light years. So they're pretty far away.
So my question is then, given that they're so far away, is there any point in really looking at them? Because we're never going to get there realistically, certainly in the next few hundred years.
That's a good question. And the answer is yes. It is very important to look at these. And the reason is that 20 years ago, we didn't know of any planet outside of the solar system. And now we have approximately 1,000 planets discovered by Kepler and many more discovered from the ground. And we are actually talking about now looking at their atmospheres, looking for biomarkers. Biomarkers are signatures of gases in the atmosphere that could be produced by life. And I anticipate that with the new generation of very large telescopes that will be available 5 to 10 years from now, we will be able to study the atmospheres of many more planets and actually be able to look at signs of life as we know it.
Absolutely incredible. Willie Torres from the Harvard-Smithsonian Centre for Astrophysics, and he was speaking with Greer Jackson.
Meanwhile, back here on Earth, the UK's Chief Medical Officer, Dame Sally Davis, has described the danger posed by bacteria becoming increasingly resistant to antibiotics as on a par with the threat from terrorism. Part of the reason for the problem is that we have only a limited repertoire of antibiotics to use, and that's because we get them by culturing microbes that normally live in the soil. But because most of these microbes won't grow using traditional lab techniques, we've not been able to unlock the antibiotic arsenal they may be harbouring.
Now, Kim Lewis at Northeastern University has discovered a new way to grow these previously unculturable bacteria. And the result is at least 25 new antibiotic compounds, one of which, Teixobactin, is powerfully active against superbugs like MRSA. Kim began by explaining when antibiotic resistance was first highlighted as a concern.
The problem began about 40, 50 years ago when it turned out that soil microorganisms that we could culture in our laboratories to isolate antibiotics from are a very limited resource. They make about 1% of the total diversity of the microorganisms, and the bulk of them are uncultured, will not grow in our lab. And so in the absence of discovering the introduction of new antibiotics, our pathogens developed resistance, and this resistance is now spreading faster than we can introduce new compounds.
Can we not just do some very clever chemistry and come up with new chemicals, try those and turn those into antibiotics?
Clever chemistry so far has largely not worked, and the reason for that is that bacteria are very well protected. They don't want foreign molecules to penetrate into their cells. Antibiotics evolved over millions of years to breach the penetration barrier. We have not yet figured out how to do that with synthetic compounds.
Therefore, your approach is to say, well, given that we've only got antibiotics from the small minority of soil bacteria that will grow in our laboratory, what about the vast majority that won't? What kinds of chemicals could they be harbouring? Can we exploit them?
Exactly.
So if they won't grow in your laboratory, how can you do that?
Well, then you do the exact opposite. We came up with a gadget that allows us to grow them in their natural environment, and that's how we get access to uncultured bacteria.
Why won't these bugs grow in your laboratory normally? What stops them?
I do not have a complete answer to that question, but one thing that we did find is that at least some of uncultured bacteria depend on growth factors that come from their neighbors. You do not know what those growth factors are. They're not going to start growing.
In other words, you need to recreate the environment that they would be in the soil more faithfully than a Petri dish is capable of doing, and that's why they won't grow at the moment.
At least for quite a large number of cases, yes.
So what does your gadget do to surmount that problem?
It's very simple. We take a sample of soil, dilute, mix with agar, and instead
This
of
is the stuff that culture dishes contain, isn't it? The growth medium.
Right. And instead of pouring it in a petri dish, as you would normally do, we sandwich it between two semi-permeable membranes that have pores, big enough for molecules to pass through, but not big enough for bacterial cells. And this whole contraption, we call it a diffusion chamber. It then goes back into the soil where the sample originated from. This essentially tricks bacteria. They don't know that something happened to them. Everything diffuses through the chamber, and they get all the growth factors that they need. And they start growing and form colonies. Once a colony forms, that colony will then start growing on a petri dish in the lab. So it looks like the main bottleneck in accessing uncultured bacteria is to get that initial growth into a colony.
Having done that, did you find some new molecules, some new compounds?
Yes. So far, 25 new antimicrobials were discovered, and the compound that we're discussing today, teixobactin, is the latest and probably the most exciting. And the bacteria that it targets are called gram-positive bacteria.
And what effect does the teixobactin have when it hits these gram-positive bugs like Staph aureus, of which MRSA, the hospital superbug, is a member, isn't it? What does it do to those bugs?
It targets a polymer that is needed to build the cell wall of bacteria. If you add this antibiotic, you see that the culture very rapidly lyses. It just clears.
How did you test it then?
We tested it in mice that are infected with Staph aureus, with a multi-drug resistant strain that is hard to kill. This compound injected into a mouse cured it of a blood infection, of a thigh infection, or of a lung infection with another pathogen that causes pneumonia, Streptococcus pneumonia.
And were the mice still healthy afterwards?
Yes.
So it looks quite promising.
It looks quite promising, and mice are not a bad predictor of how compounds will behave in humans.
That's Kim Lewis from Northeastern University. You're listening to The Naked Scientists with Chris Smith and me, Kat Arney. On to our main topic for this week now, and if you're anything like me, you may have overindulged slightly over the holidays and then be making some desperate New Year's resolutions in an attempt to undo the damage. Losing weight or just staying healthy seems to be a huge problem for some people. We're eating more than ever, living lazier lifestyles, and obesity is at record highs in many Western countries. 50% of adults in the UK, the US and Australia are now overweight, which is double what it was 2 decades ago. So why is this? And can science help us out of this mess and in to skinnier jeans?
Let's hope so. Coming up, we'll hear about a chemical that can fool you into feeling fuller than you really are, some ways that psychology can help you to avoid binging, and why our chairs are killing us. In fact, I'm keeping myself on my toes, at least metabolically speaking, by doing this show standing up. But does it make a difference? We'll find out later on. Before that, why are humans, as a species, so prone to gaining weight? And are we approaching trying to lose weight in the right way? Cambridge scientist Giles Yeo looks at the genetic and the metabolic reasons for weight gain. Hello, Giles. Good to have you with us.
Good evening.
Well, to answer these weighty questions, tell us, first of all, actually, what is fat, though? Why do people put it on, and what is it?
So fat gets a bad rap, but we really need it to survive, because fat is the group of cells that you use to make long-term energy storage, and you need it to keep you alive.
Indeed, because if we have too little fat, then women don't have any capacity to reproduce, for example. The body uses it for various signals, doesn't it?
That's correct. That's correct. So you need to have enough fat in order to keep your various biological functions going, because how much fat you have indicate how long you can last without food.
How does my body, therefore, regulate how much fat I've got?
A fat, although is there and is a storage organ, also releases hormones. And what happens is these hormones, they're called adipokines, but they circulate in the blood and they signal to the brain. So the more fat you have, the more of these signals. And so your brain is exquisitely sensitive to how much fat you actually have sitting in your body.
Therefore, it interprets how well fed you are based on the levels of those chemicals in the blood.
Absolutely. How long you can last without food.
Does that also set appetite then?
Okay, so your brain regulates food intake not only from the fat signals, which is your long-term stores, but also from the gut signals, which are your meal-to-meal variation. Okay, so what I had last time, how many calories did I have last time? It integrates these two signals and then supposedly then controls your feeding behavior. So it then influences what you then eat the next time around. The problem is, for the vast majority of our human evolution, we have been evolving in a time where there was too little food rather than too much food. So we are very, very sensitive to having too little food. And so when your brain makes you eat when there is food to make sure that you can survive.
We are therefore effectively slaves to our genetic evolution. Because we've evolved not knowing where our next meal is coming from, we are now genetically programmed to try to avail ourselves of all the energy we can.
Yes, that is actually quite accurate.
Why is it then that some people can exist in the environment that we have created for ourselves and not gain weight, whereas the majority of the population do?
That is the very, very key question. What is clear is that because the prime directive, okay, for human beings is to eat enough to reproduce. That's pretty much it. Eat enough to survive long enough to actually reproduce. All of the pressure has been to, well, what happens if there's not enough food? Whereas there has been no selection pressure to say, well, there's too much food. Well, aside from maybe the saber-toothed tiger making you too big. But otherwise, there is not a big, strong selection pressure for eating too much. So therefore, there is a more natural variation in how one responds to an environment where there's too much food.
Given that variation potential, does it mean that I might extract different amounts of energy from the food I eat than you do? So we may eat the same thing. It says on the packet there's 300 calories in this, but the amount of energy you will extract when you eat it may be wildly different than the amount that I get out of it.
Okay, I think there are two questions there. The first is, how do you deal with energy compared to how I deal with energy? So if we're eating exactly the same type of food, how you or someone else might do it, yes, there are going to be subtle variations and what we call energy partitioning. So for example, maybe you may eat a calorie, store half of it and burn half of it. Maybe I store 0.6 of it and burn 0.4 of it. Okay, that's the kind of thing that is there. So there are definitely differences between how people burn their calories. Your second question has to do with calorie counting, so to speak. And in many ways, calorie counting seems to make sense. Oh, I need to have X 100 calories in this particular meal. Because a calorie, after all, is a unit of energy. And it's physics, okay? So a calorie is a calorie. And it should be a calorie whatever you eat. The problem is how you actually access it when it actually gets down to you. So for example, when you take 100 calories of glucose, for example, and you eat it, you're likely to get 100 calories of glucose out. Whereas if you have 100 calories of celery, I think you're likely to
negative
take
energy.
Exactly, negative energy. And it is negative energy. You're likely to take, I'm making it up now, 110 calories in order to burn those 100 calories. Now, those are the two extremes. But if we then imagine somewhere in the middle where you have a processed minced beef meal, as an example, compared to a steak, the energy you need to chew to actually break down the steak compared to actually eat the slop that is there are going to be very, very different. So yes, it is the sum total of how much energy you get from a specific food that makes a difference at the end.
Thank you very much. Giles Yeo from Cambridge University.
When it comes to eating, our bodies do have a way of telling us when we're full. You know, that familiar stretchy feeling that stops you reaching for that last wafer thin mint. But sometimes that full feeling isn't quite enough to stop you from overindulging, especially maybe if you're actually on a diet. Imperial College scientist Gary Frost made the news just before Christmas due to his team discovering an ingredient you can add to food to make it more filling. And he joins us now. Hi, Gary.
Hello there.
So let's start by what actually makes us feel full when we eat. Is it just the size of my dinner?
No, it's really complicated, and we don't quite understand at the present time. There's lots of different signals that occur in the gut and just after you eat. Some of these are generated by nerves. Some of these are generated by hormones.
And what sort of things? They just send signals to our brain going, you know what, put the fork down.
Absolutely right. They do exactly that. They send signals to probably two specific areas of the brain, the hypothalamus and the brainstem, and they tell your brain that you've had enough. But, as you've just heard from Charles, the brain can override that if it sees something that it really likes.
Tasty, tasty pie.
Yeah, absolutely right.
So you're actually looking at how you can hijack this system to make us think that we are fuller and back away from the pie. What did you start looking at?
We've known for some time that deep down in your gut, in the colon, there are special molecules that are developed there by the bugs that live there. And these molecules can actually signal and release or cause the release of appetite regulating hormones from your colon. And it's that we've been looking at, is that these very small fatty acid molecules that actually cause the release of these hormones that actually stop you eating.
So it's food getting to the bugs in our gut that then make this signal and stop me from eating.
That's absolutely right. But unfortunately, in where we currently live, the actual types of food, because these are dietary fibres, the amount that we need to actually do that, we just can't eat enough at the present time. It was different if you live in Africa or somewhere where you have a very traditional native diet, but in the Western world, we don't eat close to enough to actually do that.
Tell me about how you're trying to hack this system, how you're trying to use these chemicals to make a way of making people feel fuller.
It takes a bit of clever technology which has been developed by our research partners in Glasgow, where we take those molecules, those short-chain fatty acids, and we attach them to a dietary fibre. So a dietary fibre can't actually be broken down by the enzymes in your small bowel. So what it does, it means that the actual short-chain fatty acids hitch a ride on the dietary fibre and they get all the way down into your large bowel, into the colon, where the bugs then actually chomp up the dietary fibre and release the short-chain fatty acid. And that actually enhances the amount that's there and releases the actual hormone that actually reduces your appetite.
So the idea is you could add this to food, say, our pie. If you put this in with the pie filling, then your pie would make you feel a lot fuller and you wouldn't want to eat so much of it.
Well, you seem to be a bit stuck on pies, but generally, generally the idea that this has been developed as a food ingredient, because obviously what we want to try and do, because as you've just heard, weight gain in adults is so widespread, you've got to develop systems that are on a population basis. So this is an attempt to do exactly that, is to develop a very safe food ingredient that will suppress appetite in people who are actually concerned about weight gain.
It does sound great, but where is this at the moment? Have you tested it in clinical trials? Are there any risks, for example, like could you overdose on it?
Well, the paper that we released just before Christmas, all the testing was done in humans. So we know that this works, that we see a reduction in weight gain over a 6-month period when humans are given this particular molecule. Can you overdose on it? Well, it's like any dietary fibre. If you eat too much of it too quickly, then you're going to get minor effects such as bloating. But if you're actually sensible about what you do, it has very, very few side effects.
And very briefly, have you actually tried it yourself?
Yes, we've tried it ourselves in clinic as part of the volunteers, and it does what it says, really. It actually causes a short-term suppression of appetite. So you eat it, and about 3 hours after you've eaten it, you feel more full.
That's Gary Frost, ruining my love of pie. He's from Imperial College London.
You're listening to The Naked Scientists with Kat Arney and also with me, Chris Smith. This week we're talking about weight gain and weight loss and some of the effects of being overweight. And apart from increasing the risk of developing conditions like diabetes and heart disease, gaining weight can also affect your memory, which might in turn make further weight gain more likely. Psychologist Lucy Cheek has been looking into this and she's with us now. Hello, Lucy.
Good evening.
Tell us first of all then, why should gaining weight affect my memory?
Well, it's a very complicated process and it's something that we don't fully understand at the moment. But lots of research, both in animals and in humans, seems to suggest that all the different routes you can get to obesity from, so eating a high-fat, high-sugar diet or having a genetic issue that causes you to become obese, can all lead to changes in your brain. And as Giles said earlier, a lot of the genes that we have that control our eating and how we gain weight act in the brain. And so when you change things in the brain, sometimes you can change how the brain works in a number of different ways, as well as on top of why we and how we eat.
What's the evidence that you've got that if someone does gain weight, that their memory does go off kilter? And by how much does their memory go off kilter?
So this research area is really very young at the moment, so we're still discovering things all the time. My own research over the last couple of years has looked at overweight and lean people and compared them on memory tests. And what we found is that there's about a 20% difference in memory ability between young, otherwise healthy, overweight people and their lean counterparts. We followed that up with a brain scanning study where we looked at the areas of the brain that are associated with memory whilst people are doing this memory test. And we found that the, again, young, healthy, obese individuals had less activity in the memory-related brain areas. So their brains did seem to be responding differently.
But I presume what you didn't do was to take someone slim and put them on a Bridget Jones's Diary force-feeding diet to make them gain a load of weight, and then reassess their memory to see if their memory deteriorated having gained weight, or have you done that?
We haven't done that, and that's something we'd really like to do. Obviously, that's something that takes a lot of money and resources, and you need to get people willing to come and take a high-fat, high-sugar diet.
But has anyone done the equivalent in an animal study? Because you could, for instance, force feed a mouse, just give it too much food and see if the mouse's memory suffers.
Yes, absolutely. And people have done that. So people have taken rats and put them on what's called a cafeteria diet, which is a very high-fat, high-sugar diet where they only have access to really unhealthy foods. And what they found that over time, these rats gained weight, as you'd expect, but they also showed learning and memory deficits. And they also found that they had significant changes in the bits of their brain that dealt with memory. So people have done this in animals. It does seem to have a big effect.
Do we actually know why the junk food diet is damaging memory, and is it reversible? If you slim down your mouse or your rat again, does the effect go away?
Well, so it seems that perhaps it does. The research in that direction hasn't been done quite so much. In terms of why it happens, we still don't know. The kind of leading theories are that it's to do with insulin. That even if you're not diabetic per se, if you're overweight, then quite often your insulin levels are different and your insulin sensitivity is different. Insulin, as we know, acts in the body to control how much we eat and our blood glucose, but it also acts as a messenger in the brain. And if its ability to act as a messenger in the brain is disturbed, that has a lot of effects in all the areas that rely on it to send messages.
How might this decrement in memory in someone who's gained weight affect their ability to be compliant with a diet and lose weight afterwards?
Well, actually, it's really interesting. So there's been some research showing that what we remember about what we've eaten can dictate how hungry we feel several hours later, say at the next meal time. So if we, for example, watch TV during a meal and don't remember the meal very well, then later on we can be a lot hungrier than if we concentrated really hard on the meal. And actually, if you trick people into thinking they ate a different amount than they actually ate, then you find that how much they think they ate dictates how hungry they are later on, whereas how much they actually ate only dictates how hungry they are immediately after the meal.
Lucy, thank you very much. That's Lucy Cheek. She is from the University of Cambridge. Now, staying with the world of psychology for a moment, over the holidays, Greer Jackson wondered if there are any simple tricks of the mind to help her with her New Year's resolutions.
This year, I've resolved to stop eating so much custard. But why is not eating something so much effort? It's all to do with having to make a conscious effort to stop yourself from doing something you associate with pleasure. So how do we get around this? The Food and Brand Lab, part of Cornell University, looks into the psychology of eating. I caught up with researcher Anna Tao to find out if they've discovered any handy weight loss techniques.
So the trick is to try to control the environment rather than to control yourself, because to control the environment, it takes decisions that are less on an ongoing basis, so it'll be less demanding. If I keep trying to control myself in an environment where it's difficult to do so, that'll take a lot of willpower, and at some point I'll run out and slip. On the other hand, if I make a one-time conscious effort to change my environment, because we tend to respond automatically to food and a lot of our eating behavior is not necessarily conscious. So I see the cake, even if I tell myself, don't eat the cake, that's because the initial inclination is, this is something I would really enjoy. So I'm sort of programmed to go and eat it. And I need to tell myself no. And it's an active action to override the initial inclination to eat the cake. So what we want to do is we want to remove some of those triggers for unhealthy eating. So that can be done by making eating healthy foods easier, more convenient, and making eating unhealthy foods more difficult, making the foods less visible, and if possible, making them less appealing. So I'll give some concrete examples for that. I have an insane ice cream addiction. I can't get enough. Like if there's 5 pints of ice cream in my fridge,
It'd be gone by tomorrow.
yeah, that's definitely possible. And that's kind of bad for weight control. So for instance, I could have ice cream in my freezer, but keep it in the back so that I can't see it every time I open, and then I'm less inclined to... Because once I see a stimuli, I'm going to react to it. If it's not visible, then I'm going to need to think about it independently and then get it. And that might sound like it wouldn't make a huge difference, but it would, at least for some people.
Hide the food in the back of your cupboard then, check. But what about when you're not at home? For example, eating at a fancy restaurant.
When I used to go out for dinners with my family to a restaurant, my mom would always tell me, don't eat, we're going out to dinner. But sometimes it might actually be a good idea to eat something to make yourself a bit less hungry, so you're not going to go wild once you're there and exposed to all these temptations. And also, part of what happens automatically is if a food is in front of us, we tend to continue eating it. And that's something we've seen in broad variety of studies. So there's a classic study that the director of the Food and Brand Lab did, where he had soup bowls constantly refilling themselves through tubes as people ate. And people ate a lot more when the soup bowls continuously refill themselves, because there's food in front of you and you continue eating and the plate doesn't go empty, so you don't know that you're done.
So it's like a bottomless pit of soup.
Yeah. Yeah, exactly.
How much soup did these people eat?
That I'd have to check. So this and a lot of the other information, if you want to get actual numbers, are on our website at Food and Brand Lab. If you Google Food and Brand Lab, you can easily get
I
to it.
did have a look on the website, as Anna suggested. People unwittingly ate 73% more soup when they didn't notice their bowl was being refilled, compared with people who knew just how much they were eating. What's more is that they reported feeling just as hungry, so feeling full can simply come down to paying attention to how much you're eating. This idea of avoiding mindless eating came up again.
One of the studies we recently had published had to do with television viewing, and how if someone watches a TV program that's more engaging to them, they wind up eating more. And part of that relies on mindless eating. So the food is right in front of you, you're more distracted, so you're gonna eat mindlessly to a greater extent. You're paying less attention and you're just eating on autopilot. Eating is very easy. It's something that you don't really need to think of, you just do it automatically. So making it more difficult for ourselves to eat mindlessly is one trick that people can use to control their eating. And also changing what you eat mindlessly by changing what's available.
There you have it. Hide the ice cream, display the celery, and pay attention to everything you eat. And whatever you do, don't eat from a bottomless bowl of soup, or in my case, custard.
My case is biscuits. That was Greer Jackson, and she was talking to Cornell University's Anna Tao. Kat.
Now, staying fit isn't just about your eating habits, it's also heavily affected by how active you are. The bad news is that the vast majority of us are spending way too much time on our derrieres. This is said to be by some as dangerous to your health as smoking. Dr. Michael Mosley, science author, broadcaster and advocator of all things healthy, joins us down the line now. Hi, Michael.
Hi there.
So is sitting down really a problem? I'm here in my chair. Is it really that bad for me?
Sadly, it is, because we spend, on average, something like 10 hours a day sitting down. In the good old days, people roamed around a bit and they were much more active in their jobs, whereas I don't know about you, but I spend an awful lot of time sitting down at my computer, tapping away. And the problem is that what happens is the glucose you eat in your meal, it all kind of sits rather sludgily in your body, that your muscles just don't get active enough. And there are a lot of studies now which suggest, as you said earlier, that being sedentary is almost as bad for you as smoking, and that you cannot undo the damage you do to yourself in those 8 to 10 hours sitting down by then dashing off to the gym or going for a run.
Well, now, as he mentioned earlier, Chris has been standing up for this entire hour. I've been sitting down. What sort of difference has this actually made? For example, has he burnt off more calories than me?
He has burnt off some more calories, not a huge amount, but we did a little experiment for a series, Trust Me, I'm a Doctor, and what we did is we got 10 people in an estate agent's. We took away their chairs and we got them to stand for around 3 hours a day. And we fitted them with accelerometers, and we also measured the effects of that standing on their blood glucose after eating lunch and on insulin. And there was a big reduction in the levels of glucose. The glucose returned to normal much faster, which is obviously good for diabetes. But they also burnt a few more calories, and according to our expert Dr. John Buckley, when he did the experiment, if on the basis of this, if you stand for 3 hours a day, 5 days a week, that adds up to 10 marathons a year.
Wow. Now, I'm feeling a bit guilty because I'm writing a book at the moment and I'm spending a lot of time sitting on my bottom, and lots of people work in offices every day. What can we actually do about this? I see some people who have these very trendy standing desks. How do we get more standing in our lives?
I think you have to be fairly hardcore to do that. I have not quite persuaded myself to get round to it. Lots of sort of writers used to work standing up. Winston Churchill wrote his speeches standing up, and there's a long history of it, but I think it's an acquired thing. Jim Levine, Professor Jim Levine from the Mayo Institute, is very keen, so keen in fact that he has a sort of treadmill and he works at that. But even if you simply get up every 30 minutes for 1 minute and walk around, they did this study in New Zealand where they got about 70 normal healthy volunteers, and that's what they did. The others sat for 9 hours with brief toilet breaks, or they did every 30 minutes they would get up and just walk around for 1 minute. And just getting up and walking around for 1 minute every 30 minutes made a substantial difference
So maybe
to
I
their
should
fasting
set a
glucose.
timer. Should I set a timer if I'm working? Ooh.
Completely, because otherwise you forget and you sit there for hour after hour. But set the timer every 30 minutes, get up for 1 minute, and indeed drinking lots of nice cold water is good. You'll burn a few calories, but the main thing is it'll force you to go off to the loo more frequently.
Now, for people who are, gym bunnies, I do like my gym. What is the best way of doing exercise in terms of counteracting the effects of sitting?
There are two kind of approaches. The standard one is, you go there and you trudge away on the treadmill. I'm personally much more a fan of high intensity training, HIIT. And that is becoming extremely fashionable now. And that can be as little as 3 sets of 20 seconds going flat out. That's kind of what I do. I have an exercise bike and it takes me about 5 minutes. HIIT, what it does is it does something which standard exercise just doesn't do. It increases the amount and activity of the mitochondria. And it seems to lead to greater fitness faster. I mean, what people who are gym bunnies like to do is they do standard, and every so often you put a little burst in. If you go for a run, for example, what you should do if you see a hill is sprint for 20 seconds flat out up that hill, preferably obviously not damaging yourself in the process. But there seems to be something about the intensity which is incredibly important if you want to improve your fitness.
And for people who have spent maybe most of their lives sitting on their backsides, if they think, right, I'm going to get up, walking, maybe do a bit of physical exercise, some high intensity, is it going to make a difference or is it just too late?
Oh, absolutely. Start any time, any age, and it's going to make a difference. We know that doing even, say, 20 minutes, if you go from sedentary, will increase your life expectancy by around 5 to 6 years, which works out at about 40 minutes. So 20 minutes invested now is worth 40 minutes of longevity. So it's a good deal.
Well, I feel like I want to stand up for the rest of the show. Thank you very much. That's Dr. Michael Mosley, science writer and broadcaster.
No, it's interesting because we've got a little bit of time left. We thought we'd invite all of our contributors this week to take part in a little bit of Q&A. Michael, I'd like to begin with you. Standing up as I am, Michael, doing this programme this week to prove, that it is possible to remain on your feet for more than 5 minutes and also do a job. The one thing that's striking me, though, is that this radio studio is completely set up for someone to sit down. The world we appear to have created for ourselves is one which encourages us to be lazy.
I entirely agree with you that the environment that we have created is one where all the inducements are to sit down, not to be active, basically not to move very much. This is not only true of the offices we are in, but also just getting to the office. If you want to get up to the 7th floor of the BBC where I work, the great incentive is to take the lift, because the lift is right there in front of you. If you want to go up the stairs, you have to kind of work your way around the back. And I think what we should be doing is make it much harder to take lifts. I think we should do things like slow them down, or perhaps put the smell of urine in the lift to discourage people from taking it. I was recently in a hotel in Sweden, and there they had these lovely stairs beckoning you, and right round the back was the horrible little lift. Whereas in most hotels, it's the other way around, that when you actually try and find the stairs, either they are locked or they just smell really horrible.
Yes, so we need to do the sort of multi-story effect, don't we, and make the lift very unappetising. Now, one diet that's been very popular in certainly recent months is this so-called 5-2 diet. We've had some questions in about this. What actually is the 5-2 diet? How does that work?
So the 5-2 diet is intermittent fasting. The idea is that instead of being on a sort of low-calorie diet for weeks, months on end, that what you do is you eat normally 5 days a week, and then 2 days a week you cut your calories quite dramatically, down to about a quarter of the normal level. So that would be about 500 calories for a woman, 600 for a man. And there appear to be health benefits which go beyond losing weight, because by doing so it generates a level of stress. Rather like when you go for a run, you get stressed. And some forms of stress are actually rather good for you.
Note here from Carol. She said, is it normal to get headaches on those fasting days? I must admit that on days when I've gone without food and I'm accustomed to eating usually quite a lot, she says she gets symptoms, and I certainly concur with that.
I think the main thing you need to do to avoid headaches is drink lots of water, because we get a lot of water via the food we eat. And therefore, if you're cutting down on the amount of food you're eating, then you just need more water. More water is great from all sorts of perspectives. You'll burn a few calories just to warm it up, and also it'll encourage you to go to the loo a bit more. And that means getting up, getting active and things like that. But there is no intrinsic reason. And indeed, if it happens, it should be transitory, it should pass. But headache is normally associated with dehydration.
The question here for you, Lucy, why is it so hard to keep those resolutions that we resolutely make every year and then resolutely break?
It's very hard to empathise with your future self. Your future self is a very different person from your current self. And it's quite easy to think, just as I would think, oh, well, it's perfectly fine for Chris to give up all his food, but I'm not sure if I'm willing to do that. It's quite easy to make those kinds of decisions for our future selves as well. So we tend to, on the first hand, make New Year's resolutions that are quite unrealistic. We are quite harsh on our future selves.
Not just because we're drunk at the time.
Well, obviously partly because we're drunk at the time, but we tend to be quite kind to our present selves and quite harsh to our future selves. So we make resolutions that are quite difficult to keep. On the other hand, it's also this tendency to think that we're going to be better in the future. We tend to have an idea of our future selves that they are going to fulfill all the things that we currently don't think that we can do. And therefore we put restrictions on them and say, well, okay, if I decide to do it now, then I definitely will do it in the future. But what needed to be done is to realistically say future me is not actually that different to current me. Current me is kind of lazy, so future me is going to be quite lazy too.
Giles, we've got this message here from Stella who says, how is weight loss affected by how big you already are?
That's a very interesting question. I think the largest thing about how big one is the bigger you are, oddly enough, the more energy you need, but that's not odd, but therefore the more energy you burn. Okay, and the smaller you are, the less energy you need, and the less energy you actually burn as well. So your size will determine actually your metabolic rate. So that obviously then has a big role to play in how you would then react to cutting specific amounts of calories.
And Michael, we've got this tweet here from Ikra who says, is eating late at night bad for you, or does it just matter what the aggregate number of calories across a day that you consume is?
I think broadly speaking, the most important thing is the amount of calories you eat across the day. But there is some evidence that eating late at night is not a good thing to do, because actually what you need is a period of time when you're not eating. That's when a lot of repair goes on. So if you eat late at night and then get up bright and early and start eating again, you're not giving your body some rest from food. The old idea that we should eat lots, small meals regularly, is probably a profoundly bad idea.
So this whole question of breakfast like a king, lunch like a prince and dine like a pauper, that's based on sound principles then?
It's not a bad idea at all. And there is some evidence, I've seen a couple of trials, which suggest that eating calories in the morning is probably better for you than eating lots later in the day.
Giles, Alex Johnston has tweeted at Naked Scientist, what is your view of rapid versus slow weight loss? Which is probably more effective?
I think the whole point about weight loss is not the actual weight loss. I think most of us can actually lose the weight. It's keeping the weight off. So losing it in a quick way, maybe it's more unsustainable compared to actually doing it in a slow, methodical fashion that is then possibly more easy to maintain, because it's keeping the weight off that is actually the key challenge rather than losing the weight itself.
Giles Yeo and also Lucy Cheek, Gary Frost and Michael Mosley, our guests all this week. Thank you very much. Kat.
And now it's time to close the show with our question of the week. Khalil Thurlaway took a look at this bite-sized question from Sarah.
We're always told that we need vitamins and minerals in our diets, but I've been wondering what they really are. What happens to them when they get inside our bodies, if we can store them, and what happens if we don't get enough of them?
It would be lovely if we could get by just eating what tastes good, without worrying about nutritional content. And why can't we? To feed my curiosity, I spoke to Professor John Beattie, head of the University of Aberdeen's Micronutrients Group.
Vitamins and trace minerals are more than just the spice of life. Most of them are essential for human life, but are only needed in small amounts. They all have very different jobs to do, but are essentially helping the cells in your body to read your DNA correctly, allow proteins like enzymes to work properly, and reduce the damage to your body caused by stress.
Vitamins and minerals are important for some pretty fundamental functions in your body. Alas, man cannot live on bacon alone. But what actually are these nutrients that we can't live without?
Minerals are mostly metal elements like zinc and iron, whereas vitamins are molecules made up of carbon, oxygen, hydrogen, and sometimes nitrogen.
These four elements are the most abundant in the human body. But because we don't have the right biochemical machinery to make vitamins from scratch, we need to get them from our diet. But is it possible to stockpile nutrients, or do we need a constant supply?
Some, like vitamins A and B12, can be stored in the body, usually in the liver, but others, such as zinc, must be constantly supplied in your food.
The reason that some nutrients can be stored and others can't is down to their solubility. Fat-soluble nutrients like vitamin A can be stored, whereas water-soluble ones like vitamin C are too readily excreted to keep hold of. What happens if your supply runs out or your intake isn't enough? Scurvy-ridden pirates and Victorian children with rickets spring to mind.
Severe deficiencies can cause dramatic visible effects, such as loss of hair, skin sores, birth defects, and even death. But mild deficiency may cause, for example, slow growth, poor eyesight, weak immunity, and decreased resistance to cancer and heart disease.
Wow, scary stuff. Sounds like vitamins and minerals are pretty important then. I hope that answers your question, Sarah. Next time we'll be off to the land of Nod, searching for an answer to this question from Alberto.
If you fall asleep and start dreaming, but you dream you're awake, do you still get a good night's sleep?
Well, if you would like to speculate on that one, having slept on it first, of course, then you can email chris@thenakedscientist.com. You can also find us on Facebook, or you can tweet at Naked Scientist. You can, of course, also join in the debate on our forum. That's at nakedscientist.com/forum. That is it for this week. Thank you very much to Georgia Mills for production, with help from Khalil Thurlaway and Danielle Blackwell. Join us next time when we're going to be having a duvet day. We'll be exploring the wonderful world of sleep. The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust, the EPSRC and the STFC. My name is Chris Smith, and thank you very much for listening. Until next time, goodbye.